In 5.3 electric cells, we're going to look at cells, and you may recall that when we have a few cells that are sort of stacked end to end, we'd call that a battery. Now, cells supply energy to a circuit because of the chemicals that are contained within them, and the process there is that those chemicals undergo a reaction, and so chemical potential energy is converted to electrical energy, and that's because in those reactions we'd have bonds breaking and being reformed, and that can also then produce electrons that can then move through the circuit themselves, and as a result that's how we have energy being transferred through the circuit. So electrical energy from chemical potential energy, and that's then transferred through the circuit by those charge carriers, which are in this case electrons. And we need to have a look in a bit more detail at how that process occurs and how long it's going to take, because the chemicals that are present in a cell are not going to last forever, and so we're going to see things about the capacity of the cell itself and how long it can allow current to flow. Before we get to that though, we need to have a look at two different types of cells. So the first is known as a primary cell, and with a primary cell we have the condition that chemical reactions that are going to occur in the cell itself will continue until all of those chemicals are used up. And because of that, we can then refer to a primary cell as being a single-use cell. So with a primary cell we can only use it once, so your typical battery, once you've used it you then have to throw it out. The other type of cell is a secondary cell, and with a secondary cell, those chemical reactions that occur can be reversed. And so by allowing those reactions to occur, we have that conversion of chemical potential energy to electrical energy, but we can then reverse those reactions, and basically it's just by pushing current through it in the opposite direction, and so those chemicals are returned to their original state as electrical energy is converted back to chemical potential energy. Note though that this only can be done with secondary cells. We can't force current through a primary cell and expect it to return to its original state. There are some reactions that are reversible, but not all. So don't try recharging a non-rechargeable battery. You'll find that it doesn't work, and you run the risk of actually causing the battery to blow up. So a secondary cell, as I've just mentioned, is pretty much just a rechargeable battery. So a battery that can be restored to its original state and used again and again. The next aspect of cells that we need to look at is the idea of capacity. And capacity, it's not its EMF, it's how much charge it can release. So the capacity of a cell is its ability to release charge. So to give you a bit of context around that, as an example, if we had two 9-volt cells, so those cells provide the same EMF, but imagine that we had one of them if it has twice the chemicals than the other, then it will last longer because it has more ability to release charge, because there's simply more charge in the chemicals that are available. Now, to relate to the quantity of capacity, we need to go back to the equation for current, so I being equal to capital Q for charge over time. We're going to rearrange that to write it simply as Q is equal to I multiplied by T. So previously we had Q being the quantity of charge. here we're going to say that Q is the capacity. And in a bit of a break from the usual units that would be used here, we're not going to state them in SI units. Capacity is usually either stated in amp hours or milliamp hours. I is the current, and that will still be in amps or milliamps. If we state the capacity in milliamp hours, then the current would usually be measured in milliamps, and T is going to be the time, and now it's going to be measured in hours, not in seconds. Let's have a look at a quick example here again. If we had a AA battery, they usually would have a capacity of about 2 amp hours. So that means that they've got a certain amount of charge and can be used then for a certain length of time. And easiest way to think through this is to not worry too much about an equation so much as just looking at the quantity itself. Imagine that we have then a circuit that draws 20 milliamps of current. Then we can calculate how long the battery will last by going back to that idea of the capacity. So 2 amp hours, we can break that up into 2 amps for a duration of 1 hour. That's the easiest way to think of the idea of amp hours. That means that the battery is going to provide 20 milliamps of current for some duration, we'll call it X hours. So just looking at ratios here really. So now if we wanted to figure out what X is equal to, all we need to do is take the 2 multiplied by 1, divide it by the 20 milliamps, but we need to keep the units consistent here. So if we've got 2 amps on the left hand side and milliamps on the right, we need to convert that milliamps to amps, so 20 by 10 to the negative 3, and so that would give us a value of 100 hours. So that battery is going to last 100 hours in this particular circuit because it's only drawing 20 milliamps. Now if the circuit was drawing 40 milliamps, then the battery would only last 50 hours. So the more current that's being drawn, the shorter the battery life. Now while the capacity allows us to figure out how long a battery might last for, it doesn't necessarily mean that the current's going to be consistent the whole time, and that's because as a battery discharges, or as a cell discharges, we're going to see a variation in EMF. They don't usually provide a consistent EMF for their full duration. So we'll have a look at a graph here that shows that. So this graph shows the discharge of the cell on the vertical axis over time on the horizontal axis. Now there are 4 key points to note here, so I'm going to go through and annotate them. The first is this starting value, and that's the initial EMF. And the initial EMF is the highest that it's going to be throughout the lifetime of the cell. And you can see then after that point it continues to drop, and so the initial EMF is usually going to be higher than the stated value or the stated EMF. So if you go and buy a 9 volt battery, what you'd find is that that initial EMF that you might measure is going to be higher than 9 volts. We have this first period of drop off through here, so this is then the next phase. We have a significant initial decrease here. And by significant, it's not necessarily a huge percentage, but it's certainly a significant decrease in that first initial phase. So we see that decrease once the cell starts to be used. For the next portion though, so we're now sort of going from this region up to around about this line here somewhere. It's not a hard and fast thing on a graph, it's just more an indication of the majority of the cell's lifetime. So this part here, so for the majority of the cell's lifetime, it's going to provide a fairly stable EMF, but not necessarily exactly what the stated EMF is, but it's approximately in that sort of value. So again, if referring to a 9-volt cell, you would find that throughout this range it's going to be pretty close to 9 volts. It might start up a little bit above it, but then it's going to fall just slightly below it, but it's still going to be close to that 9 volts. The last region then is from here through to the end in this significant decrease. So in this portion here, we have a rapid decrease in the EMF. And that's as all of the cell's chemicals are being exhausted. There's no more chemical potential energy that can be converted to electrical energy. So there's the discharging of a cell. The last thing then is to have a look at what happens when we charge a secondary cell. So with charging a secondary cell, while we can return the chemicals to their original condition, it doesn't mean that they're going to be returned to 100% of that original condition. So the chemical reactions that occur, I mentioned this earlier, they can be reversed by forcing current to flow in the opposite direction. And that means that we actually need to connect the battery in reverse, in a sense. And so instead of having the positive terminal releasing current, we're going to then flip it around so that the positive terminal has current forced into it. And as a result, then the chemicals are going to be restored simply because we're forcing the reaction to go in reverse, and the electrons are sort of reforming the bonds that were there to begin with. I mentioned earlier that not all chemical reactions are reversible, so we can't just use any battery as a rechargeable battery. There's only certain chemical reactions that can be used. Now with each recharging, we're going to see that the capacity of the secondary cell won't necessarily return to its original state. And we'll see that there's going to be a bit of a lifetime of how many times it can be recharged. And again, we've got another graph that we can have a look at there, and just showing it's not so much one that we need to annotate, it's more just one to have a look at. So you can see with this graph that shows the cycle life of a rechargeable cell that it starts off at about, say, just below 4.5 amp hours, and over time with each successive recharging, you can see that there's a little bit of variation as it travels through, but ultimately we get this decrease in the capacity of the cell, so that after it's been recharged around 2,000 times, the capacity is now down to maybe 3.7, 3.8 amp hours. So with repeated rechargings, that's going to decrease, and eventually it'll start to drop off, so that the rechargeable battery is now not really usable. You might notice that with things like phone batteries. With repeated rechargings, the capacity of the battery has quite significantly degraded, so you might need to be charging it every half a day, whereas previously it might have been that you could recharge it once every 2 days. So there's all the ins and outs of cells. We'll then move on to look at some of the other aspects like internal resistance of cells as well.